want to say something else, which I've not described as yet, which is an important feature about the remote future, and that is black holes. It's very important because it's where all the entropy goes in the remote future. This is a picture, a space-time picture of a black hole. People usually represent it by a black blob, which doesn't tell you very much. But if you put the light cones in, you really see a lot of what's going on. I'm not going to spend too much on this picture, but you see the cones tip over in such a way that they become, the outer side of the cone becomes tangential to this cylinder at the top. That is the event horizon, and you can see that a particle which falls in gets trapped and it cannot escape. So this is a conventional picture of collapse to a black hole. Now, what happens to black holes in the remote future? What happens is, well, this is, first of all, I put the black holes in the picture now, so it's not really to scale now anymore, but never mind. Those are now the lines representing the singularities. I should have said that the Big Bang is considered to be singularity, where curvatures go infinite, and the black holes have singularities in their middles, which is where curvatures go infinite. That's where I mark things in red. But never mind too much about that. Now, what happens to the black holes? Well, according to Stephen Hawking, if you wait long enough, then these black holes will start to radiate away. They will radiate away. To get a picture of this, there are a lot of black holes which are very, very big, supermassive black holes. Our galaxy has a black hole in its center which is about 4 million times the mass of the Sun. It's a relatively small one from some other galaxies. There is the Andromeda galaxy, which you can see in the night sky. The Andromeda galaxy has a black hole which I think is about 40 times bigger than ours. Never mind. The biggest ones which we seem to see, how long would you have to wait? You see, the universe has to expand and get colder and colder and colder. This radiation is very, 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 very cold. If you have to think of the hottest temperature you ever get in these things, you have to compare it with the coldest temperature ever made on the Earth. But when the universe expands and expands and expands, it gets very, very cold. And then the black hole becomes the hottest thing around, and then it evaporates away by Stephen Hawking's black hole evaporation. Now, the biggest ones, actually probably not the biggest ones, it would even be longer than this. But how long would it be? Think of a googol years. What's a googol? It's not a very scientific term, but think of 1 followed by 100 zeros. That's a googol. You write it all out into an ordinary notation, that would be a googol. Now, if you wait that many years, some of these supermassive black holes will have gone off, bang, pop, or whatever it is. Some of them won't have. They take an awful long time. But we're talking about infinity. Infinity is a lot longer than an awful long time. So these things will all disappear. Now, the crucial point about this in my picture is that although that radiation spreads out and spreads out and spreads out, if you remember that picture, I don't know if I've got it here. You see, I've got them going off pop here. The actual final disappearance of them is a relatively boring thing. I called it a pop. Okay, you can think of it as a nuclear explosion or something, but cosmologically it's really very, very trivial. Almost the entire mass of that black hole, which could be the entire mass of a galaxy, it probably will ultimately be the entire mass of a cluster of galaxies. Galaxies tend to be in clusters. Ours is a relatively small one. There are lots of bigger clusters of galaxies out there. And their supermassive black holes will finally swallow each other up. We are in a collision course. Our supermassive black holes are in a collision course with the Andromeda galaxy's black hole, and they will spiral at each other, and there will be some explosion when that happens. I'll say a little bit about that, but I want really to talk about the Hawking effect, which is really what I'm talking about. So let me go to the next picture. You see, can you observe? I used to talk about this thing, and I'm thinking that there's probably somebody telling me how much time I have left. 5 minutes, is it? Thank you. I used to think, I gave lots of talks for a while, and thinking that nobody will ever be able to prove me wrong, so I can talk about this forever. However, I then began to think of, well, maybe there are observational effects. Now, this picture is showing you one of them. These are a collision between supermassive black holes. The horizontal plane in the middle is the join between the previous eon, which is before that thing, and our eon, which is above it. And this is us right at the top, looking back, that's our light cone, and seeing the effect of supermassive black holes in the previous eon colliding. And I'm not really want to talk about that, but this is a picture of my colleague Vahe Gursajan plotted out lots of these things in the sky, and they form a very uniform, non-uniform distribution. You see these things in the sky. Nobody believes me because the sky is not to be, you're not supposed to see irregularities like that. A Polish group headed by Krzysztof Meissner, Paweł Nierowski, and another Pole, and subsequently a Korean called Daniel An did some analysis. This is I should say the first one was the Planck data, the WMAP data. That was one satellite sent out. This is a more sophisticated satellite called the Planck data, and you see that it's still very, very non-uniform. People didn't like that because they didn't link the non-uniform. I didn't want to go too ahead. Can we go back just for a second, please? That one showed the concentration of the centers. Well, let's go on to this picture. Now, this is now something else. Now, below that plane, you see the bottom, the red plane, is the crossover between one eon and the next. So we're seeing supermassive black holes finally evaporating away, and you have to imagine that Google years, if you like, but remember the Escher picture I showed you? Right up on the edge, you see those angels and devils, or the fish, or whatever they are, get very, 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 very tiny. So that everything that happens, even though it's a long, long time, is squashed into a tiny point. So the supermassive black hole, the entire radiation of that supermassive black hole will be concentrated into a point. And we now, just Vahe Gursajan and I, by using one method of analysis, and the Polish group using another method of analysis, seem to see these points. Now, it's mainly the Polish analysis which I'll talk about because they give a figure to it. They looked at, first of all, at the WMAP analysis, and they found a confidence level that this is a real effect of 99.4% confidence. Now, they looked again. This is perhaps a good picture of, let me just explain what I was just saying a minute ago. They looked again, and they found these Hawking points with a 99.98% confidence. So it's pretty clear they're there. They are seen both in the WMAP and in the Planck data. The 5 most prominent points are in exactly the same places. This picture is just to give you a cartoon. The bottom line is the crossover between the previous eon and ours, and you see the Hawking, the evaporating black hole, producing a big explosion. As all the energy in that black hole's radiation comes through, it spreads out. The next line is what you see. That's the cosmic microwave background. That is 380,000 years after the Big Bang. And a point spreads out to 4 degrees in the sky. So when you see these spots, which are 8 times the diameter of the moon, that is what you see. That's you looking back, you see not the point, the Hawking point is the point at the bottom. What you see is the spread out spot out to 4 degrees in the sky, which we claim is the result of a Hawking point. Now, maybe there's some other explanation which somebody will come about, which tells us, you see, you can't have inflation in this picture. It would spoil the whole picture. It would have to be explained in some other way. I haven't heard of any other explanation, so I'm leaving you with this. This is what I'm claiming we are actually seeing. We're seeing the spread out in the 380,000 years where a point at the Big Bang becomes what you see in the microwave background spread out to 4 degrees. Thank you very much.